Go ahead and take a minute and make sure that you can figure out the full and condensed configuration for nickel. Raise your hand if you want another 30 seconds to finish the configuration. I don't know. That's why it's scratched out. I like how I have you guys trained that you see that orange, you're like, it's got to be a click on. Not really anything to plug in. I guess you can do the configuration. True. I'm not focusing on those in this class, but there's definitely exceptions where the 4S fills before the 3D half fills are fully filled.
You can think copper one of them. I don't know about new. I think it's like 4S one and like 4S.
I think that's chromium and copper. Did you get my email?
Yeah, the printer, Caroline suspended it. Do you want me to make a copy of it, or?
So I had, raise your hand if you don't have one of the worksheets for today.
Oh, man.
Yeah, so it only printed out like 10 or well, like 20.
Do you have a blank one? I couldn't make a copy of it. She looked like she deleted the printer.
Right answer one, and then you make copies from the
Thank you so much.
Thanks, y'all. Okay, so let's talk through how we fill in the atomic orbital diagram. Can someone tell me how they determine the full electron configuration? You may have used the atomic orbital scheme, or you might have used something else. Natalie, is that you raising your hand? Say it a little bit louder. Sorry, it's hard to hear. So how did you figure out that all those are... Great. So I would argue that you didn't use this. You used one of the many other approaches to get the configuration. And so you said, I know that nickel is what? Okay, so this is the D block in the middle here. The first set of Ds that we fill are 3D. So these are going to be 3D electrons. So how did you know whether you backfill then 3D and then you just go to 3P or do you use 4S? Why? Okay, so 4S is in the S block. 1, 2, 3, 4 is where potassium and calcium are. The other way that, one of the reasons I really like to use atomic orbital diagram is because it does show you that although n equals 3 has 3s, 3p, and 3d, it's actually lower energy to put electrons into 4s before we fill 3d. That's why there's this kind of discontinuity, this weirdness where you think that 3D would be up a line higher in period 3. Remember, left to right are periods. And then if we go across the periodic table, those are called groups. As you guys probably had some fun in the pre-class quiz dealing with. Sorry about the challenges there. It really likes to have ion afterwards, which makes sense. You can't just say sodium, because sodium isn't an ion, so you have to say sodium ion. Okay, so we have 4s and then 3d. So then you started basically up here, and you said, how many electrons do I have in 3d? Okay, so if we find nickel, we count 1, 2, 3, 4, 5, 6, 7, 8 in. So then we're putting 8 electrons there. Okay, so we have 3 full orbitals, 2 half-filled orbitals. And then what do we do to complete the rest of the diagram? Okay, so we can backfill all of these. How do we check to make sure that's right? What if we messed up? What if it's actually 4D instead of 3D? What's the thing that we need to do to make sure that that's right, Caleb?
Count the number of electrons.
How many electrons should we have?
28.
How did you determine 28 electrons?
Nickel has 28 protons, and it's not showing that it has charge.
Great. So 2 things. 28 is the number of protons the nickel has. We could just say the element with 28 protons, it is nickel, so either way is fine. And that there is no charge, so we know that it has 28 electrons because it is a neutral charge. So we need to make sure that if we filled all these, that this is 20 electrons, and then we have 8 extras in 3D. Yes?
In the 3D, with those 2 unpaired electrons, would those be considered valence electrons?
So valence electrons is typically not a term used with transition metals. So with transition metals, there's a lot of other things they do, but bonding in the typical way that we think about is not really the usual terminology. So the term valence electrons, we're going to be talking about the s and the p electrons past the last noble gas. So we're going to be talking about valence electrons if we're in groups 1 or 2, or if we're in main group 3 through 8.
So the 4s would be the only valence electrons in nickel?
Yeah, but you wouldn't really talk about valence electrons for anything in that transition metal area. And so it's kind of a moot point because these are all transition metals. Joey?
How exactly will we write the condensed?
Okay, so let's go ahead and write the full, and then we'll write the condensed. So the full is, what do we say, 1s2. Natalie, can you read it out?
1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d8.
All right. And then how do we look at that? Can I? 3p6. D8. Come on. Get with it. It is 8, right? Okay. You know when you're like thinking about the next question, you're just writing what someone said? Hopefully you're not doing that too much when you're in this class. Like I'm doing.
Or at least if you do it.
So then can I get another volunteer to talk about how we figure out the condensed electron configuration from this? Bria?
To do condensed, you looked at the last noble gas right before it, and then you take it. So it was like argon, then 4s2, 3d8.
And so what I'm going to do is I'm going to do square brackets around each one of the noble gases in here. So what's this noble gas electron configuration?
Helium, neon, argon.
And then there's not another one that's complete past that. So we're going to go ahead and say argon, 4s2, 3d8. Jackson?
To be honest, I'm kind of happy that you chose nickel instead of copper because copper's electron configuration has been weird.
Yes. So there's a few that are strange electron configurations. We're not going to spend class time on them. I have to be very specific on what we spend our time on today because you have a lab next week that I need to prep you for today.
Why does the book show a lot of like argon, 3d8, 4s2 in that order?
Yes.
So sometimes it'll show the D before the S.
Correct.
So it depends on where you look, whether they say you should do it in order of the shell first. So 3, 3, 3, and then the 4s. I'm completely fine with either one of those as long as you know the one you fill first is 4s before 3d. You can write it in either order. It would be inappropriate to have 3d with a lot of electrons and nothing in 4s. As Jackson was pointing out, there are some exceptions where there's some that actually it's more stable to half fill the 3ds than it is to have 4S completely filled. So sometimes you'll see 1 electron in 4S and 5 in 3D, or 10 here and 1 there. So when you have, there's a couple of elements that you'll run across that will be anything under copper, anything under chromium. Those ones are going to have half-filled 4S's, or the S instead of the D's. So keep an eye out for that. We're not going to spend a lot of time on justifications of that. Yeah, I love tricking you. Did everyone see the previous exam that I posted to Blackboard? And there's some other resources up there we talked about last class that are available for you that you should not print and disseminate or sell. Okay? So feel free to utilize those to practice. Remember that Google Sheet that I have linked to our Blackboard page gives you some ideas of which activities will be very helpful for you to figure out the material to a deeper level by going through those Pogo activities. All right, last thing before we move into learning objectives and go forward. We had talked about exam dates, and I'm required to give the American Chemical Society exam, so that means that is going to happen on December 5th. There's no question about that. That's a 2-hour time block. I'd originally mentioned that I might try to do our alternative final exam, which is the one that I will write, on our last day of class. I then realized that that's less than half the amount of time, and I don't think you guys want to try to take a cumulative semester exam in 50 minutes. So I have looked at the final exam schedule, and what I found was this, that there is a large blank here where no one has final exams on Monday, December 10th from 8 to 10 a.m. There's nothing scheduled. If you have other professors who are thinking like me and giving something on that day, check immediately and let me know. If you've heard from any of your other professors. If that comes up as a conflict, let me know. I know there's at least one person in here who won't be able to take it that time, so I will try to find an alternative time, but I'm not obviously allowed to schedule anything here for the whole class. And so this is a spot in which I believe we should be able to have a second possible chemistry final exam. The higher the 2 scores is the one that will count towards your class grade.
So the whatever test that you have to give us, what does that count for?
If that's the only one you take, that's your final exam score.
Why do we have to take it?
Why do we have to take it? So we, as a chemistry department, compare ourselves to national averages and what other schools are doing.
It's comparing, seeing if you're teaching and we're learning.
Well, both of them are, yes, but one of them is on a standardized test. But the standardized test includes all topics.
Yeah, that's what I'm saying.
Some of those are topics that I'm not emphasizing. Yes. So it has to be a one-size-fits-all for the national test. And I want to make sure that the grade that I give you is not based on a one-size-fits-all. It's based on what we prioritize in this class. Yes?
Will the standardized one be curved?
No, there's no curving. I do not curve because that means I don't expect the assessment to align with what you do. I expect my assessment to be what you guys are capable of and what I've taught you to do. And so then everyone gets 100%, everyone gets 100% in the final. I'm happy with that. It's totally cool. If I curved, it would mean the average would be 70, and I'm not going to do that. So if you have a conflict with Monday, December 10th, 8 to 10 a.m., please send me an email. Whenever that conflict may arise, please put it in your calendar. So December 5th is our required exam at 10:30 a.m., right? I think this is how this calendar works. 10:30 to 12:30, Wednesday, December 5th is a required final exam. If you do not take that final exam, you do not get to take the one on the 10th. The department requires us to do that one on the 5th. Okay? Any questions on final exam schedule? Lenny?
You told us that there are 2 exams that we might can take. So one is the national one, and the second is the come from you.
Yes.
My question is, if I, for instance, I took the national one, and then
I will try to get you scores back immediately from that. Once you have that score, you can decide if you want to take the second test or not.
okay. So when that the national one will be held?
The national one is in our scheduled time slot for this class. Because we have a class at 10 a.m. Monday, Wednesday, Friday. Our final exam is going to be December 5th at 10:30 a.m. That is the required. You must be here at 10:30 a.m. December 5th taking the final exam with us. If you then also choose, you can take the December 10th, 8 a.m. final, which is the one I will write. Any more logistical questions on that, please email me or post it to Canvas discussions. I want to make sure that we have time to get into class. And is it all right if I come around and chat with you afterwards?
Yeah, do the same.
Okay.
Thank you.
All right, so our goals for today, we hadn't done transition metals for writing electron configuration, so I wanted to make sure we got a chance to practice that together. So that was one of our learning objectives, is to be able to write electron configurations for transition metals. And then the rest of the class time is really going to be spent on justifying the trends of the periodic table that you guys have worked on a little bit outside of class, talking about why those trends come about. And then next week, our lab is going to be about modeling, not like the fancy New York modeling. We're talking about like building models and looking at molecules in 3 dimensions. So that means that we're going to spend a little bit of time at the end of class thinking about Lewis structures. Has everyone completed the chem tour? Raise your hand if you're still not finding the additional non-graded components on OWL. So there's a chem tour, about a 15-minute thing about how to draw Lewis structures. Raise your hand if you did not find that. I want to know if that was a common thing that people did not find. I see a couple hands. Is that you just don't want to raise your hands?
Yeah.
Okay. So is it that you didn't see them on? Okay. So what's that, sir?
I didn't see them.
All right. So if you look at what's due today, for the people who did complete it, did it show up as something that was due for you today? We got to fix this. We got to figure out how, when I post something you have to do before class, that it shows up and you know what it is.
Were there just 2 quizzes for today?
Yeah. There are 2 pre-quizzes, but did anyone do something on Lewis structures and drawing Lewis structures? Was that listed as being due today?
Yeah, it shows it, but it's not going to grade it, but
Correct.
it's like practice, I guess it says, and then it shows that yes today. And then it just says like practice if you go to all assignments.
So how are some people seeing this and some people not? Does anyone know?
If you go to all assignments and you're looking for more, you'll probably find it.
Well, I don't want, so I put it as due today so that you wouldn't have to go to all assignments. So I'm curious.
I believe if it's not graded, it's not going to show up as...
So I've gone to the student view to check that, and for me it shows up, but that doesn't mean it shows up for you guys. I believe that it's not showing up. I need to fix that. Do I send an announcement out from now on if there's a video or something you have to watch?
Yes.
Do you guys get Blackboard announcement that I send out? If you don't, please make sure to change your settings, or manually go look, because more than likely I'm going to be sending out an announcement a couple times a week. Okay? So then it is imperative that before lab next week, you complete that chem tour. It is listed as being due today. It will take you probably about 20 minutes. It gives you some foundations for how Lewis structures are drawn. Maybe you already know how to draw them, but this should give you an additional approach for doing that. All right, so let's go to this question. This is the end of our class, last class. Click in your answer for this, and then chat with your neighbor once you have that to try to figure out. All right, I think we've got just about everybody clicked in. How confident do you all feel in your answers? Let's see, thumbs up, sideways, down. By the way, when I pull out my phone, I'm pulling up the instructor side of the clicker app to see if I can see the question. Sometimes I can, sometimes I can't. I'm not texting in the middle of class. So we have a pretty strong consensus about this answer? Let me make sure that that is actually... So a lot of people are answering A. That as we go across from hydrogen to lithium, sodium... Wait, so it can happen when we move down a group? Okay, great. I thought we had a different question up there. I'm really glad we don't. Because that answer would be terrible for the question set. Okay, can anyone justify why it is that when we look and we go down a group, why it is that the radius might increase? Mode?
You have more and more electrons, well, electron shells as well.
Which one is it? Is it electrons or electron shells that makes the biggest difference in size?
I think it's the shell.
What do you guys think?
Shell.
Yeah. So it's a really big deal. It's a really big difference talking about the number of electrons, which is a lot of times the first response. So there's more electrons. It's going to occupy, probable to be occupying more space. And that is problematic when we start talking about going across a period, which we'll talk about in a second. So as we go from the top of a group and we move down, this is a diagram that shows in picometers, 10 to the negative 12th meters, how far across the probability of finding an electron is, right? That electron shell. So if we go from 1s to 2s, it gets a lot bigger. Sodium is even bigger yet. Potassium's bigger. Rubidium gets even bigger. So, okay. And so the main justification for this trend that you just saw was that you have more shells to fill more electrons. We know that each shell is successively larger than the last one. Now let's talk about when we move left to right across the periodic table. Once you have your answer, talk to your neighbor. Interesting. I guess the concern would be thinking about following the direction. Cool. How confident do we feel in our answers here? I see a total mix all over the place. And we kind of see that here. There's a distribution of these answers. So why is it that the radius is going to decrease as we go across a period? Let's take a look at our sizes. Lithium, beryllium, boron, carbon. Talk to your neighbor. Why is the trend that the atoms get smaller and smaller and smaller? Because one of the most common arguments is we're adding electrons. It's going to get bigger. We're adding electrons and it doesn't get bigger. So talk to your neighbor and try to figure out why that is. Okay, so everyone's got really quiet. That means we have some really good explanations. Did anyone have a light bulb when they were talking to other people and were like, oh, yeah, that kind of helps, that explanation or that thought process? Kayla? it relates very much to the ionization energy. I think I might state it the other way around. The ionization energy depends on the atomic radius. And so we'll get into that in a minute. Anyone else have like kind of an epiphany of like, oh, I see, that kind of makes some sense? Well?
Because there's a greater number of photons, but the amount of shells is usually inconsistent because it's just S and T. So the greater positive charge attracts the shells more and more because when you get closer.
You guys hear what he's talking about? So he's talking about, Love is saying that in this particular group, we have electrons in 2s and 2p. So they're in the same shell. And as we fill those shells more and more, we're putting more and more electrons in. Yes, we might think that the radius would get bigger. But at the same time, that shell, that 2s and 2p, we're also considering now one more proton and one more electron. Another proton, another electron. And so as we go all the way to the right, we have a significant number more protons, but we're in the same shell. So what you think about, the way I think about it, is it kind of like pulls everything down tight, and it kind of keeps those more compact and more compressed when we're in those shells. Then what happens when we go to the next element? What's the next element past neon? The next atomic number past neon is sodium. Is that atomic radius bigger or smaller? Bigger. So we're going smaller, smaller, smaller. All of a sudden that next one's bigger. Why is that next one bigger? Amber?
Because it's the next shell being added on.
Great, so now we're in n equals 3, 3s. And we only have one electron in there, and that whole n equals 3 shell. So I want you guys thinking about what we expect for the size of that atom, and then what does that mean about how tightly those electrons are held? How tightly are these electrons held to the nucleus? If those electrons are equal in charge, negative charge, and they're much closer to strong positive charge, think about how hard it is to pull one of those electrons away, ionization energy, which Kayla was referring to, versus if they're floating much further away. Moed?
Does the addition of the P shell not affect the size?
It does affect the size a little bit, but we also end up with, so if we're talking about across there.
Like if you were on P1, it would increase the size, but is the like attraction of the extra electron great, like big enough to make it still condense?
So if we just look empirically at the trends, what do you think? So these are 2s are being filled, here's 2p. So this is the gap between. It's kind of like we cut out the transition metal space between them, right? So we see a decrease in size.
So would it be the same for the d orbital or the d?
So let's take a look at the whole set. And this one does not show transition metals and their sizes. And I think that there's some variability in there where there's some spots where it does spike up.
Right.
But I want us thinking about what's the overall trend. What are we most likely to see as we go from left to right, top to bottom, bottom to top, whatever direction we're talking about, where are we most likely to see an increase in atomic radius and a decrease? So I don't have that image specifically handy, but you can Google image it, and I think you'll see that it overall trends, but there's a couple of little bumps in it where it doesn't, the d orbitals don't quite hold the exact same trend. So there's a couple spots there on the worksheet, I think, where I asked you to talk about as we go from left to right. Let me see. Across a period, what happens, and then when we reach a noble gas, what happens. So I want you to kind of take notes as far as how you can rationalize it in your head, how these things fit together, and how that allows us to predict the size of an atom. If I were to give you two atoms in the same period, how would you justify which one is bigger? So maybe take a couple notes there at the bottom of that first page. That would help you justify which one is bigger and why. That is a very likely exam question that I would give you. That type of thing of what's the rationale behind which one is bigger. so then last class we were talking about, well, we can sometimes find an ion of a lot of these elements. I want you to, every time you look at the periodic table, if you hadn't done so before, I want you thinking S block, D block, P block. Specifically, what charge are we going to find in each one of the different groups if we were to find that as an ion? And now we're going to talk about what the size of those might be if we were to find those ions. So I think at the top of the next page is this clicker question. Which one of these elements in the isoelectronic series would you expect to have the largest radius? All right, we have 43 responses. Make sure to click in your answer. Which one of these do you think is going to be the largest? So let's see what our responses are. All right, a lot of people here are saying sodium plus is going to be the largest. Before we get into the details of why that might or might not be, what does isoelectronic series mean?
It means that they have the same number of electrons.
Great. Okay, so if we were to write the condensed electron configuration for all 5 of these, what would they have in common? What would be different? Amber?
They would all have the same number of electrons as neon.
They would all have the same number of electrons as xenon, and hence the condensed configuration would be the same. For neon, sorry. I'm on today. Neon. You have a question, John?
I mean, they'd have different number of protons.
Great, okay, so the main difference between all of these is that they have a different number of protons. So if we think about electron configuration of xenon with different number of protons.
You said xenon again.
Dang it.
You can change it to xenon and we'll follow it.
Have to change the number of different things. So what I want you guys to do now is with those 2 pieces of information, the same number of electrons as
Neon.
same number of electrons as neon, but all of them have a different number of protons. Think about which one you think is going to be the smallest and which one is going to be the largest. Talk to your neighbor. Votes open again. Re-click in your answer. We want to come to consensus. Yes. What you say? Same, but maybe for me it's easier to think about which one's smallest. So that's why. Maybe that's All right, click in your answer for this question.
Yes.
You're just gonna roll with it. That's no luck.
All right, let's see what you guys answered here. Okay, a lot of changes, but still a lot of discrepancy, right? 50, 25, 25. Would anyone like to justify their answer? Avery.
So my logic for it was to go and apply the same concept we just used to talk about radius to go across,
because we were talking about having more electrons than protons, and then that allowed us to be bigger, where the more protons to electrons we had, the more they were sucked in. So if you're going with the...
Careful, all of the ones across the period have the same number of protons and electrons.
Yeah.
Right? Each one is neutral, so there's some similarities there.
Yeah, but then when you have the, okay, so when you add the 2 extra electrons, basically there isn't enough to suck them in and go back out. Was the summarized version of how I thought that.
Okay, great. Can anyone add their description as well? Savannah?
Well, I know that the atomic radius decreases whenever you're moving across a period to the right. And so with that logic and the logic that with another energy shell you have a bigger radius, I chose sodium plus.
Okay, but do we have an additional energy shell? What is the electron configuration for all of these, Josh?
Since they're all right around neon, right? That's the electron.
They all have the identical electron configuration of neon.
That's a simple way to put it. Yes. When I first read it, I did not go up the next orbital shell. Sodium and magnesium, they were off the block because the electrons were not there. So we were still back in neon's electron number, but oxygen's already larger. So it had less protons, so I was like, boom, oxygen. That's what I did.
Okay, so I'm going to tweak. I think I'm going to pull pieces from what everyone's saying and kind of add them together. If we have a set number of electrons, we have xenon's electron configuration. It's a noble gas configuration. Neon. It's very stable. I just love xenon today. If we have that stable electron configuration, is 8 protons going to pull them closer to the nucleus? Or 20 am I saying 8 or 12 protons going to pull those electrons closer to the nucleus?
12.
The more protons we have, the more those same number of electrons are going to be pulled in. So does that mean that magnesium is going to be the largest or the smallest of all those?
Smallest.
So then the largest one of all those is going to be the one with the least pull in the nucleus on that same number of electrons. We only have 8 protons. So those same number of electrons, those 10 electrons, aren't going to be as tightly pulled to the nucleus. So in that isoelectronic series, the one with the least number of protons is going to have the least pull and going to be the largest. All have the same number of electrons. We have less protons, so we're less capable of pulling that in. So that's something you have to figure out how to put in your own words. Take notes underneath. Either I need to come back to this and try to figure out how to explain this, or thoughts now how you have to explain that logic, because that's going to be really important when you do a couple other things. There are no additional electron shells added for any of the isoelectronic series because they're ions. So all of these have the exact same electron configuration. I can write it fine. So the basic trend is that whenever we have an ion, having less electrons means it's smaller, having more electrons means it's bigger. If we look at each individual atom...
Wait a second. Lithium plus, that's the same electron configuration as helium. And helium is smaller than 76 millimeters.
But we have an additional... I have to think about that. What are the numbers for helium?
I think he was put up there that it was like 32.
Okay. So the trend that I want to highlight here is that going from neutral to +1, we're always going to get smaller because we're taking electrons out of that outermost shell. If we're adding electrons, we're going to be increasing the size of that volume in which we're likely to find those electrons.
Beryllium acts in the way you'd expect at least.
Yeah, it's a lot smaller. Not sure what the deal is with lithium. All right, so now let's talk about ionization energy.
So,
what is ionization? Wait, question before we move on.
So in that case, oxygen would be the most electronegative, right?
Fluorine is the most electronegative, but
I mean,
oxygen
when it has 8 protons and 12 electrons. Out of those right there, since it's the biggest one, it would be the most electronegative?
It has the most electron density, so that is not necessarily electronegativity. Electronegativity is how likely it is to pull electrons towards itself, how likely it is to move towards achieving noble gas configuration, and fluorine is more so that way. So we'll kind of touch on that a little bit later next week.
Yeah, there's this video about fluorine that shows like
dinosaur.
Cold, like cold gas and cold charcoal briquettes, and as soon as it touches, it sets itself on fire. That's not a joke either.
So now we're going to be talking about ionization energy. Can someone remind me what ionization energy means? Trey? Not Trey. Tyler, sorry. Trey. Tyler.
That's right.
Love us how you're raising your hand. Ionization energy?
It's like energy that the nucleus pulls on the electron, or is that amount of energy used to ionize?
Yes. Second one. Tripti, you want to clarify?
It's the amount of energy used to remove an electron
From?
the shell.
Okay, so if we have a neutral atom, we have neutral helium. How much energy does it take to remove one electron? So what charge does it go from and to? If we're talking about ionization energy. It goes from a charge of 0, neutral, to a charge of +1, because how much energy does it take to pull that first electron away from a neutral atom? That's our definition of ionization energy. And you'll notice this little 1 here. Some atoms have more than one electron, and so we can talk about, well, if we remove a second electron, then how much energy does that take? For right now, we're focusing on the first electron. We're going from neutral to +1 charge. And this energy is listed in kilojoules to have a whole mole of that atom to take an electron away from all of those.
That's a lot of energy just to remove.
It is. So go ahead and think about this question. What do you expect to happen to the ionization energy when we go from lithium, beryllium, boron, carbon, nitrogen to go across a period? Do you expect it to become easier to pull an electron from a neutral atom, or do you expect it to become harder to pull an electron from a neutral atom? Talk to your neighbor about this one.
That's always just like, right?
All right, can I get a fresh voice, new volunteer? Which answer did you choose and why? Logan?
So I chose A because you're going to cross the period, you're going to need more and more to break it apart because the bonds are going to be stronger.
So careful, we're not getting into bonding yet, so we're not going to use that word, but the attraction maybe is a better word for that. So the attraction is going to be stronger and stronger. Why? Why is the attraction stronger and stronger for an electron as we go further right across the periodic table?
Well, as we described in the as the trend of the size of the atom, so as you go across, it's going to get closer and closer because you're going to have more electrons and protons, the ratio, so they're going to get closer. So
And they're in the same shell. Okay, great. So thinking about the smaller the atom is, the atomic radius is, that means that the closer positive and negative charges are to each other, it's just like two magnets, right? The closer two magnets are together, the harder it's going to be to pull them apart. Same thing with a positive and negative charge. So as we go across the periodic table, it's kind of written vertically here. So we go helium to neon, right? Going from left to right across period 1.
Neon?
Helium, hydrogen to helium. I need some more coffee. We see that helium is much more difficult to remove an electron from than from hydrogen. Why is lithium so much easier to remove an electron from than helium? Eric?
Helium is in noble gas state.
Great, so helium is a noble gas. It means it has a full shell. Lithium just has one electron and one s. It has a very large atomic radius relative to it. It's much easier to pluck that electron away. And then as we start going right, deviation for boron.
Oh.
But overall, we have a trend that as we go to the right, across a period, the radius gets smaller and it becomes more difficult to take that neutral element and make an ion out of it. We can look at the periodic table. Once again, they cut out the transition metal in this because transition metals are kind of wonky. But we can see that as we go lithium, beryllium, boron, carbon, nitrogen.
PI, I think it's supposed to be thallium.
And then we see
TL.
We see all these guys as we go from left to right. There's a general trend that the smaller the nucleus is, or the smaller, the atom is, the more difficult it is to remove an electron from. Here's another way to look at it, and this shows all of the elements. If we look at, to orient ourselves on this graph, our x-axis is the atomic number. So if we're looking for neon, it's 10 protons. We'd go up and see, why does that not line up? It's very interesting. Should line up with neon. All right, so regardless, as we go from left to right, we have increasing atomic number. And then this shows how hard it is to pull an electron from that nucleus. Which ones in this graph show to be the hardest to pull an electron from? Can someone circle it on the iPad? Which ones are the most difficult?
Did I miss any?
Finally, got to say xenon and be right. Okay, so xenon is one of those. What do all those have in common? What do all the most difficult elements to remove an electron from have in common? They're noble gases. They have full electron configurations. They have octets. And the easiest ones are all in group 1. And then in between, we see this periodicity. Periodicity means things happen in repetition. And so we have difficult, easy to difficult, easy to difficult, easy to difficult. We see the transition metals are here in yellow, and we see a little bit of fluctuation there. Eric?
It tends to happen in the third and sixth groups where they drop. So, they also just drop a little bit.
Yeah, where there's a little bit of a deviation from the trend. So that's something that we will talk about in office hours. Because I don't have a direct answer, it's more complicated than a quick answer. Yes. For today. By the way, I have office hours today at 1. If you're not feeling completely comfortable with exam material, come hang out. That's what I'm there for. I'll stay as long as you guys need. Vote?
Because the first two, like say lithium and then VE, they have they start going up in the trend, but that's because we go to two s orbitals, and then they drop because in the orbital there's only one electron.
Yeah, but if we go, so that it definitely has to do with filling the S versus the P, but I think that there's a bit more going on than that as well. But we can think about half filling and fully filling different shells. And then some of the transition metals as well actually have different way of filling the orbitals, and so that ends up being the difference too, like half filling, as we talked about before. So let's talk now about, let's talk specifically about beryllium. We talked before about removing the first electron. I want us thinking about removing this first, second, and third electron. Which one of those do you think will be the most difficult to remove? If we do one at a time, right? Going from 0 to +1, +1 to +2, +2 to +3. Check with your neighbor. All right, submit your answer.
Yeah.
We're out of time. So let's take a look. What does this trend actually look like? Here's a visual representation of the relative amounts of energy it takes to remove the first electron, called IE1, the second electron, IE2, and the third electron. Why is that third electron so much more difficult to remove? Grant? Once we take away the first two electrons, those are the valence electrons. Now the electron configuration of beryllium plus 2 is helium in square brackets. Now we're digging into the core of electrons that come from a noble gas configuration, and that requires a ton more energy. And so we can kind of look across the periodic table. Beryllium we just looked at, much harder to remove that third electron. Why is it much harder to remove the fourth electron for boron? Fifth electron for carbon, sixth electron for...
Because those are the valence electrons, and once they go, they have an octave.
All of the things on the left side of this red line are valence electrons. It's not that they're easy to remove, but they're much easier to remove than once we get on the other side and start pulling out those core electrons. All right. Ionization energy is the last thing that will be on the exam. I thought we'd get into Lewis structures a little bit today. So this is, everything we've done this week is on the exam on Monday. Your note card can only be 3.5 by 5. If it is not that size and handwritten by you, I will confiscate it. So please make sure it's 3.5 by 5, handwritten by yourself. Feel free to ask any more questions on Blackboard or come talk to me.